So I'll get it done this weekend, I promise. So you see where we're starting? I know that we didn't finish part 5, and kind of like yesterday's lab was basically part 6, so follow the bouncing ball. But I have in my notes this is kind of how it happens at this point in the semester for this unit. So we're going back to part 3. And then we are going to go to finish part 5. Whoops, sorry. Nope. And then we're going to go to part 5, and we're not going to finish part 5. And so I'll remind you when we get there. But today, all I want to do is part 3, and then to the assignment slide in part 5. And then I want to skip the rest of part 5, which is ionization energy and electron affinity, because Monday, then, I want to start with covalent compounds. Okay, getting ready for Lewis structures for Thursday's lab. So, and you guys know that after Thanksgiving, the Thursday after Thanksgiving, you have your unit exam in here. Okay, so I know. That coming back from Thanksgiving, that's rough. We just kind of accelerate towards the final. So I kind of smile, like, how big is an atom? You're like, how could she make this complicated, right? How big is an atom? Now, again, don't blame me, and I'll try to kind of explain why atomic size does what it does. But it seems like atomic size should just, if you get more protons in the nucleus, the atom gets bigger, right? Not necessarily. So if you take just that group A elements and squish them together, the main group elements, so those 2 columns and those 6 columns, squish them together, take out the group B elements. Here's the trend you have. If you go down the group, they get bigger. Atoms get bigger. That's awesome. Okay. Now, as you go across the same period, okay, actually, as you go from left to right, they get smaller. In other words, if you want them to get bigger, you have to go from right back to left again for the atoms to get bigger. And I'll explain why that is coming up. Mm-hmm.
So it's the opposite of their energy?
It is the opposite of the number, I don't know about energy, but it's the opposite of number of protons in their nuclei.
Because we had a slide similar to this about energy, and it was...
That was electron affinity.
Oh,
yeah, it is
okay.
the opposite. Well, electron affinity, yeah, it is. It is the opposite, because electron affinity goes like this. Yep, electron affinity, like, does an atom want to have electrons? Okay, like that. Yep, and this one goes like this. So, yep, it's just the opposite. Okay, all right. So how do we say how big an atom is? Okay. Well, I have this example of a chlorine atom to show you. The video worked in my office. Okay, I think. Okay, so you're going to see some values for how big an atom is in terms of the atomic radii. So the radius of an atom basically is you take the nucleus, you start at the nucleus, and you go out to the edge of the electron cloud. So the radii of a sodium atom, 157 picometers. Okay, oops, sorry. The atom itself is 186 picometers. Okay, you kind of get the idea there. So these are the group A elements all squished together. You have your 1A, 2A, and then kind of a break, and then 3A through 7A. The halogens are not shown on here. Now, I was looking at this at my office, and you always like to kind of poke at the rules, right? But if you're like me, there are some exceptions. So like, for instance, okay, that one, if it's getting smaller, it goes 83, 77, 71, 66, which is fine, but then it goes up to 71. So it's not an exact trend. And you could probably kind of see some kind of subtle things. But just in general, you definitely see it where it gets larger if you go down the group, and it gets larger in general as you go across the period from right back to left again. So this is kind of looking at the same information. The radius of the atoms in picometers by atomic number. You kind of see these breaks, and these breaks actually go by periods. So if you find lithium, lithium is period 2. Okay, and lithium ends with fluorine. Again, we're keeping those rare gases out. Period 3 begins with sodium, ends with chlorine. Okay, period 4, potassium, bromine. Okay, so these are all different periods. And, yeah. But now these actually also include the group B elements, the transition metals. Okay, so this whole trend of the atom gets bigger as you go down the group really kind of makes sense. I think when we talked about an atom, one of the things we said about the electron is in the electron cloud is the electron actually gives volume to the atom. Okay, so basically as you move down in the group, okay, you're adding a whole bucket full of electrons. Okay, so that makes sense. The second trend, the size of decreasing, if you go from left to right, why do they get smaller? Okay, that's actually something I want to further explain. And I'm going to explain it in terms of what the electrons are doing with regard to being attracted to the nucleus and what the electrons are doing with regard to being repulsed from each other. Okay, so it's all about electrons that gives you the size of the atom. Okay, so again, about electrons. Now this slide could have been kind of cleared up a little bit. So we're all talking about attractive forces with regard to electrons. So if I go ahead and, I don't know if I want to pick on an element. We picked on carbon a lot. Let's go ahead and do that. So the carbon nucleus has 6 protons, okay? And I'll have 6 electrons out here. Let's go ahead and start organizing them, shall we? Okay, we know that we have 2 electrons in the 1s. We know that we have 2 electrons in the 2s. And then we peter out with 2 electrons in the 2p. Okay, so there are my 6 electrons. Okay, so when it says attractive forces, and I think I'll go ahead and I'll show you why in a minute, but I'm going to pick on actually those 4 valence electrons. We know carbon's 4a, it's got 4 valence electrons, there's where they are. So I'm going to go ahead and do E, E, and E, E. Okay, so as far as attractive forces, I'll go ahead and make those in red. Those would tend to go ahead and keep that carbon atom nice and small. Those are your attractive forces. Repulsive forces, I'll make them in blue. Repulsive forces are actually, well, maybe I better pick purple, because blue is my kind of shell. So repulsive forces are actually between the electrons. They repulse. They're kind of a fluffing out sort of thing. The same charge wants to repulse each other. And so actually, repulsive forces are going to make it larger. Larger, smaller. So it's a balance, okay? Repulsive forces make it larger. Attractive forces make it smaller. Actually, I think that's on my next slide. So attractive forces, what we're talking about here are the electrons being sucked in or attracted to the positively charged nucleus, the protons in the nucleus. When we're talking about repulsive, we're talking about electrons repulsing from each other. Okay, and then like I said, I emphasized smaller for attractive and larger for repulsive. All right. So I went ahead and picked on, it looks like period number 3. This is period number 3, skipping along. How do they get smaller as you go from left, as you go from right to left? No, darn it, as you go from left to right, final answers. Left to right, they're getting smaller in terms of their radii. So if they're getting smaller, then what is kicking in is the attractive forces, and actually that's how I'm going to explain it in terms of. So I'm going to do it this way. Okay, as you go this way, okay, they're getting smaller. And what does smaller mean? Smaller means the attractive forces must be increasing. While I have these up here, let's kind of double check why this seems a little bit odd to us. The number of protons in the center of a sodium atom, it's atomic number 11. So let's see. Well, it's 11, 12, cool, 13, 14, 15, 16, and 17. Okay, so those are the number of protons. And so the number of electrons, if they're neutral, and these are all neutral, are the same. Okay, so you'd be like, how come 17 electrons around a neutral chlorine atom is smaller than 11 electrons around a sodium atom? That's kind of what we got going on here. Okay, so there must be something, some sort of attraction for that chlorine atom. So before I kind of explain that, I want to take a minute just to look at your transition metals. A lot of times we see trends in the main group elements that kind of fall apart in the group B elements. And here's kind of to show you that they fall apart. So the period, or the group B elements, of course, start here. Okay, so this is your group B. So the higher it is, the larger the radius. Okay, so back to the whole asplanin part. Why is chlorine smaller than sodium? And I'm pretty sure Petrucci addresses this and calls it what I learned it as is effective nuclear charge. The symbol for effective nuclear charge is Z star. Okay, Z star. Kind of reminds me of Sagittarius A star, but Z star. And actually, just a minute ago, I said, what is Z? We learned Z actually is the atomic number of protons. So effective nuclear charge takes into consideration basically what the nucleus is. I have some examples here. Actually, years ago, I'm like, I'm going to write this down. But I have a formula. It's like a little subtraction. What you do to calculate effective nuclear charge is you take the number of protons in the nucleus, and from that, you subtract the non-valence electrons. Okay. So I can't decide where to do this. I'm going to go ahead and I'm going to make this slide go away and get a clean slide here in a minute. But if I just pick on carbon, for instance, here's what it looks like. We said carbon has 6 protons in its nucleus, okay, and those 6 electrons would be arranged like this. We have 2 electrons in the 1s, 2 electrons in the 2p, and 2 electrons in the, darn it, you know what I mean. 2 electrons in the 2s, final answer, and 2 electrons in the 2p. So you guys would hopefully tell me that these are your valence electrons, right? Okay, so your non-valence electrons are right here. So the effective nuclear charge of a neutral carbon atom, and this will make more sense on the example I'm going to do, but just for carbon, is 6 minus 2. The effective nuclear charge is a positive 4. Okay, so that's how you would do it. Now let me show you an example of, and the ones I have in my notes is I pick on magnesium and phosphorus, okay, in period number 3. I'll show you how those inner electrons actually shield the, they have a shielding effect. Let's see. Here we go. All right. So let's pick on magnesium. And let's do a similar thing that we did for carbon for magnesium. So magnesium is atomic number 12, so it has 12 protons in its nucleus. It has 12 electrons, and they are configured this way. 1s2, 2s2, 2p6, and it peters out at 3s2. Okay, So in this case, hopefully you would tell me that it has 2 valence electrons. That's where they are. Has 2 valence electrons, so the inner or non-valence electrons are 10. 10 inner electrons. Okay. So what we say is these, how do I say this? Oh, let's do the Z star next. Okay, so the effective nuclear charge, according to that little formula, is equal to 12. Sometimes I'll go plus 12 to kind of emphasize it's positively charged. Minus 10 is equal to plus 2. Okay. So here's how the effective nuclear charge works. I'm going to go ahead and draw these 2 electrons out here. Okay, those are my 2 electrons in the 3s subshell. Those, each independently, those electrons feel a tug of plus 2. Let me see, what color do I want to go with? The effective nuclear charge is 2 or plus 2. They independently feel a tug towards a plus 2. Well, that's cool. That is the attractive force that those 2 valence electrons feel. All right, let's stay in the same period and skip all the way over to phosphorus. Phosphorus is a 5A nonmetal, so we're thinking it should have 5 valence electrons. But anyway, phosphorus has 15 protons in its nucleus. Okay, and then it must have 15 electrons. They're arranged 1s2, 2s2, 2p6. Then we get to our valence electrons. We completely fill the 3s subshell, so 3s2. And then we peter out at 3p3. Okay, cool. So like we did above, let's go ahead and identify. Notice that, not so surprising since they're in the same period. Oops, I kind of got a little carried away there. Notice how many, what we call shielding electrons it has. It also has 10 inner electrons, 10 nonvalence electrons. So if we calculate the Z star, or the effective nuclear charge, that is equal to a positive 15, because that's the number of protons in its nucleus. Again, minus 10, okay, equals a positive 5. So now up here for the nucleus, I'm going to draw a Z star equals a plus 5. So again, these 5 valence electrons, okay, we have 2 here, 2 here, sorry, 2 here, and 3 here. Kind of independently, they feel an attraction towards the nucleus, which is a plus 5. Okay, so this is why they are much more attracted to the nucleus than the 2 electrons in the magnesium. So I kind of tried to show that the stronger attraction by making kind of a thicker green arrow. So that, if that is stronger, attraction is stronger, you know what that means. If the attraction is stronger, it means it's a smaller atom. And that's it. Effective nuclear charge. Do it for you every time. But for me, and you've seen, you know, actually I have my notes, I drag them out, you know, twice a year, whether I need them or not. It's not something that just intuitively I'm like, oh yeah, that's how that works. It's something that you can think through and you're like, oh, okay. So the inner electrons, the non-valence electrons, act as a shield to kind of dampen the effective nuclear charge of the nucleus. Okay, and they dampen kind of 1 to 1. For every shielding electron, you kind of dampen it 1. Okay, so that's how that works. Whew. Pretty good. So I'm going to pull these up, but these will be due on Monday. And we are going to go ahead and get to that other assignment slide. But this shouldn't take us too long since we did this part. These are not too bad. My hints are kind of general. It's funny because I was thinking, you know, there are some topics in academia where you can basically totally BS your way through. Chemistry usually isn't one of them, but these kind of wordy problems, you probably could BS your way through. I'm not a good BSer, okay? But for some of them. So the first one says, basically, I'm going to give you, or it gives you a pair of atoms and asks you which one's bigger. And so my reminder is to locate them on the periodic table. If you have to do this for a test, wink, wink, find them on the periodic table, okay? And then make your judgment. The next one, okay, explain why, and this is back to the effective nuclear charge, explain why the atoms don't get larger when you go across increasing atomic number, just like I picked on, you know, if you took notes, you can do the whole magnesium phosphorus thing if you want to. Why does phosphorus get smaller? The next one, individual atoms can be, oh yeah. This was kind of like, how do you know what the to me, the outer edge of an atom is? Well, there's a little bit of play in where the electron is. That's what I thought. Number 13 is similar to number 9. So, which is the smallest atom in group 13? Oh, I hate those new designations. They've probably been out for 15 years. Okay, so 13 actually looks like it's 3A. And see, they call those B. Oh my gosh, I noticed that. And then B is different. Basically, arrange them from smallest, which is the smallest in these atoms. Okay, you'll be fine. All right. So let's see, if I click here, does it work? It should. We rehearsed this. Okay. So now can you find this slide kind of midway into part 5? This was where we left off. Then we're just going to the assignment slide, which isn't too far away. Lots of pictures. Okay. So I really like this. If basically the electrons are what makes the size of an atom, then remember what a cation is basically a metal, usually giving up an electron. So the cation is always going to be smaller than its parent, okay? And then an anion, what is an anion? Basically an atom picking up an electron or two, so it's going to be larger. It makes sense, and I got some examples here. Okay. So kind of we just did this slide, what makes the size of an atom? It's its electrons, and its electrons have two options. Basically, electrons can be attracted to the positively charged nucleus, or electrons can be repulsed from each other in an electron cloud. And this is like deja vu. I'm like, didn't we just do this slide? Okay, yeah. So if your attractive forces increase, is it on there? If your attractive forces increase, then it gets smaller, and if your repulsive forces increase, it gets larger. All right. So sodium, we know, loses 1 electron to form a +1 cation. Magnesium loses 2 electrons to form a +2 cation. And in doing so, their cations are smaller than their parent neutral atoms. I buy that. Looking at something that forms an anion, chlorine actually picks up an electron to form a -1 anion, and it's larger, okay, than its parent. And this is just to kind of prove to you, these are the metals losing electrons, and they're smaller. These are the non-metals gaining electrons, and they're larger. I love the gold atoms. I'm just saying. Okay. So now here's kind of a little bit of a catch. We talked about isoelectronic species. I love that term. And these things are all isoelectronic with, it looks like, neon. These are all isoelectronic with neon. Oxygen picks up 2 electrons to be like neon. Fluorine picks up 1 electron to be like neon. Sodium loses 1 electron to be like neon. Magnesium loses 2 electrons to be like neon. Okay. So we could be tasked with, and you might be surprised with this. You thought effective nuclear charge was interesting. This is kind of interesting. So you might be saying, well, of course magnesium's going to be bigger because magnesium, the center, the magnesium plus 2 cation, still has 12 protons. You're like, dude, all right, it's got to be bigger. Not so much. If we take a look at each one of these, okay, again, we recognize that there are 10 electrons. Each one of these have 10 electrons, so we were okay with that. Okay. So if they have 10 electrons, we need to think of those 10 electrons, forget effective nuclear charge now, just look at the nuclei of those species. We need to think of those 10 electrons being drawn into the nucleus, okay? So the 10 electrons are going to be drawn into 8 protons. Compare that to the other extreme. Those 10 electrons are going to be drawn into a positive charge of plus 12. Okay, so here's how that looks. In the case of oxygen, we have 8 protons in its nucleus, and we have, I'm not going to worry about breaking them out into shells, but just basically you have 10 electrons being drawn into there, or individual electrons, whatever, versus the nucleus of 12 protons, and I guess it does make a difference that those electrons, 10 electrons, are configured exactly the same way. And does this not look like more, this is more attractive forces? More attraction here? Actually, we're going to see that the magnesium plus 2 cation is darn smaller. It's the smallest of everything. More, I should say most, attractive force. And we could do the effective nuclear charge. It would be the same thing. So, yep, your smallest is your magnesium plus 2 cation. Then your second smallest is your sodium plus 1 cation. Then your next smallest is your fluoride ion, F minus. And then your next smallest is, which is your largest, is your oxygen, your oxide ion, oxygen 2 minus. Again, the catch here is they're all isoelectronic. I just like saying that word. It should be on your test. Now I'm going to have to make sure it's on your test. Okay. Oops, did I miss a slide? Nope. Okay, and this is what their radii are in picometers. Okay. So then this assignment is due also. And we'll take a look at it. It's not too bad. Just those two are due. 9, 14. Looks like this. So remember, hydrogen actually can appear twice on my periodic tables anyway. Hydrogen actually can kick off its 1 electron and become a H+. It can actually also pick up an electron and become an H-. Of course, with 2 electrons, it's got the electron configuration of helium. So your first question basically is, how would you expect the sizes of those two things to differ? Well, I don't know, right off the bat, I'm thinking a naked nucleus, I mean, that's got to be pretty small. You know what I'm saying? If the electrons make the size, there are no electrons for a hydrogen plus 1 cation. So, whatever you guys think. Again, this is kind of where you just, and you should get used to just, you know, especially if you stay in school, you should be used to kind of explaining. The next one, arrange these in order of increasing radii. And my hint there was I would go ahead and, for a couple of these problems, I would do kind of like we've done. I would go ahead for each species, write the number of protons in their nuclei, and then write the number of electrons, and then kind of go from there. Okay, I think anyway. I guess you probably should find them in the periodic table too. Oh, see, this is where I actually made these a while back. So I really kind of told you the answer to this one, because bromine and selenium are in the same period, and I didn't know we were going to cover part 3 before we did that. So this is where it feels weird, but actually bromine is smaller than selenium. So we just talked about that. The last one, or the next one, again, you kind of have, looks like 5 species, and you're supposed to say, arrange them in order of increasing size, and you're supposed to kind of comment as to why that would be. I think this is neat because actually, again, it's like the example we looked at with regard to being isoelectronic to neon, or just a minute ago. These are all isoelectronic to argon, or krypton. I think, is that it? Okay. Okay, so that's as far as I wanted to get today. It's only 2:33. Happy Friday. So what did I say? Oh yeah, so we're gonna start in basically part 7 Monday, part 7.